If you're stepping into machine learning engineering, there are some terms you will hear so often they will become second nature to you. Today I'm going to walk you through those 22 essential machine learning terms, each explained simply. So let's get started. Weights are the core parameters of a neural network. They decide how much importance each input feature has. For example, in house price prediction, location may weigh more than the size. At the start, weights are random and predictions are messy. Through training, optimizers adjust weights step by step. This fine-tuning makes the model smarter with every iteration. Think of weights like the volume knobs on a music system. Each knob controls how loud or soft a feature is. As you play the music, you hear and adjust it accordingly. Bias shifts the model's decision boundary. Without it, the model might be too rigid to fit real data. Think of drawing a line through points. It won't always pass the origin. Bias gives flexibility by adjusting where the line starts. During training, bias updates alongside weights. Together, they allow the models to fit patterns better. Think of this like the base setting before any adjustment. Imagine predicting salary. Some people earn even with no experience. Bias adds that starting point for predictions. Without it, the model might always start at zero. Activation function decides whether a neuron wakes up or stays quiet. Think of it like a light switch. It turns on only if the input is strong enough. Without activation functions, networks stay linear and limited. Functions like ReLU, sigmoid, or 10H add nonlinearity. This lets the model capture curves, edges, and complex shapes. Training ensures the right neurons light up at the right time. That's how deep learning gets its power. Loss function tells us how far off the model's guess is. It's like a teacher marking your test in red ink. High loss means too many wrong answers. Low loss means the model is getting closer to correct. During training, we try to shrink this error. It's the feedback system for learning. In regression, mean squared error is the commonmost loss metric that we use. The higher the loss, the worse the prediction. Cost is the average loss for the whole class and not just one student. It shows how well the model is doing overall. If the cost is high, the class or the model isn't performing well. Training aims to reduce this number with every round. Optimizers work directly to lower the cost. It's like checking the overall class performance and not just one test. Optimizers are like GPS for the model. They guide weights in the right direction to reduce errors. Simple ones take small steps and advanced ones take smart shortcuts. SGD and Adam are common optimizers. During training, they handle all the adjustments. They keep the model moving toward better predictions. Imagine rolling a ball downhill until it finds the lowest point. That's gradient descent. It searches for the lowest error. The slope of the hill tells which way to move. Weight shifts step by step opposite to the slope. This gradually improves the prediction over time. It's the backbone of model training. The learning rate controls the step size in updates. Too high and the model overshoots the minimum. Too low and the learning becomes painfully slow. A good learning rate balances stability and speed. Think of it like a ball going downhill. Learning rate decides how big the ball steps are. Too big and the ball overshoots the valley. Too small and it takes forever to reach the bottom. A good learning rate finds balance, fast but stable. Sometimes the rate changes as training goes on. It's one of the most sensitive hyperparameters. An epoch is one full round through the data. A batch is the entire dataset given at once. Mini batches break it into smaller groups for efficiency. Each mini batch helps the model learn gradually. After many epochs, the model improves steadily. It's like studying chapter by chapter until the whole book is done. An iteration is one mini step of training. Each time the model sees a mini batch, that's an iteration. If you have 1000 samples and batch size 100, you get 10 iterations per epoch. Every iteration updates weights a little bit. Do thousands of them and the model becomes accurate. Think of it as practice rounds in a long game. Momentum is like pushing a heavy shopping cart. Once it's rolling, it keeps going forward. In training, it remembers past updates to avoid zigzags. This makes the path to the best solution a lot faster. Overfitting is like memorizing exam answers instead of understanding. The student scores 100% on practice tests, but fails when questions are new. Models that overfit work great on training data but fail in real life. Regularization and early stopping helps avoid it. The goal is to generalize and not just memorize. Underfitting is like a student who barely studies. They can't answer practice questions or exam ones. The model is too simple to learn patterns, and the accuracy stays low everywhere. Fixes include adding more features or complexity. Regularization is like telling students not to overcomplicate answers. It penalizes unnecessary details. Techniques like L1, L2 or dropout keeps the model simpler. Simpler models usually perform better on new data. It's like trimming off distractions to focus on the core. Sometimes training too long makes things worse. Early stopping is like knowing when to stop practicing. We watch the validation set to decide the right time. once performance stops improving, training halts. This prevents overfitting and saves resources. It's an easy way to get a just right model. There are many types of models for one problem. Model selection means choosing the best fit. We compare results using the validation data. If the model is too simple, it will underfit, and if the model is too complex, it will overfit. The best model balances both. It's like picking the right tool for the job. Accuracy is the percentage of correct answers. If the model got 80 out of 100 right, accuracy is 80%. It's simple and easy to understand, but it fails if data is unbalanced. For example, predicting always healthy in 99% healthy data gives 99% accuracy. That's why other metrics are also used. Precision asks of the predicted positives how many are actually correct. It's vital when the false positives are costly. Think of diagnosing cancer. The wrong positives can cause panic. Precision ensures predictions are trustworthy. During training, it's optimized alongside the recall. Together, they define classification reliability. Recall verifies did it caught all the real yes cases or not. In disease detection, missing a sick patient is dangerous. So recall ensures you find as many true cases as possible. High recall means fewer misses. During training, recall is tracked with precision. It's about coverage and not just correctness. F1 score combines precision and recall into one number. It's the harmonic mean balancing both the sides. It is specially used in imbalanced datasets. For example, fraud detection often uses F1 score. It avoids the traps of using only accuracy. Training often optimizes F1 for fairness. Confusion matrix table breaks predictions into 4 parts: true positives, true negatives, false positives, and false negatives. True positive is when the model correctly predicts a positive case as positive. On the contrary, the model correctly predicting a negative case as negative is known as true negative. False positive is when the model incorrectly predicts a negative case as positive. And false negative means when the model incorrectly predicts a positive case as negative. R-square, mean square error, and root mean square error are used as performance metrics in regression tasks. Mean square error squares the error, so big mistakes hurt more. Root mean square error is just the square root of the mean square error. It is easier to read in real units. R-square shows how much of the data's variation is explained. Together, they reveal how close predictions are to reality. And that's our full list consisting of all the machine learning essentials. If you found this video helpful, drop a like, subscribe to the Naughty Samurai channel, and comment which one should I deep dive into next. I also have a machine learning series which is ongoing and which is completely free. So if you feel like diving into that, feel free to check that out. Until then, stay sharp and stay naughty. The Naughty Samurai signing off.